All right, we're back to type 1, type 2, type 3. Keep in mind, what we did in the last videos, we talked about how do we get air in here. I'll address that a little bit more as we go on. But once we've got atmospheric air in here, we have to get the O2 to here. So how do we do it? Well, here's the type 1. Type 1 is a squamous epithelial cell, flat, kind of looks like a bent fried egg. We don't want a lot of distance in between here and here. We don't want cuboidal, we don't want columnar, we just want pure squamous. Type 2 is a little bit different. It doesn't look like a squamous. And what it does is it secretes a material called a surfactant. And here's the deal with surfactants. If you want surfactant, get a bar of soap. Get some Dove cleaning kitchen stuff. Soap is a surfactant. Here's what this is all about. This is lined up with water. It's completely covered with water. Just a little thin layer. Water is polar, as you know. Polar loves polar. So what polar is going to do, water is going to do, is it's going to grab more water, and these little air sacs are going to collapse. Surfactant is an interface between polar and non-polar. So what it's going to do is it's going to keep these from essentially collapsing on themselves, which is good, because if those start collapsing, then we can't do gas exchange. So we got type 1, gas exchange, type 2, surfactant to keep this open, and then this thing that down here, it calls it a dust cell. It's a macrophage. It's essentially a white blood cell that's meandering around, and anything that has gotten through all of the other defenses is now going to hopefully be eaten. Now we've gotten this far. We've gotten a lot of this anatomy in. What we have to do is address how do we get the gases in there. And this gets us to what we call Boyle's Law. Now, Boyle's Law, and don't worry about this, I'll try and explain it a little bit easier, I hope, in a couple of minutes. Boyle's Law is going to explain how we start to do this gas exchange and how we get essentially the air into the lungs and ultimately into the alveoli. Typically, when we just relax, when we just sit, I'm going to back up here a little bit. And we have inspiration and exhalation. Every time we breathe, it's about half a liter that goes in, that goes out, goes in, goes out. But there's a residual volume. That residual volume is what's stuck up here. If you're up here, I'd ask a quick question of everyone that's in here, and there's nobody. Okay, if you're up here, do you do gas exchange? And the answer is no. You have to be in an alveoli. So there's air that comes into here that we can't do gas exchange for. I had a situation a number of years ago. I was scuba diving and I started doing very, very, very rapid shallow breathing, and I was bringing air into about here and back out, and here and back out, and I couldn't breathe. It's because it didn't get down to the alveoli, and that's where we have to have it. So we've got this essentially tidal volume and then this little residual volume that doesn't do us any good. Now let me go back to Boyle's Law. Boyle's Law essentially is this. If you take any gas, and that's what we're talking about, we take a gas and we compress it, the pressure goes up. Yeah, that's what this means. So volume goes down, pressure goes up. So essentially it means this. If I am going to push my diaphragm up and I'm going to constrict my intercostal muscles that are around my ribs. What I'm going to do is shrink down the volume of my pleural cavity. Makes sense. According to Charles Boyle, if I shrink the volume, the pressure goes up, which means air shoots out of my mouth. At the same time, if I relax and I increase the size of the pleural cavity, what's going to happen now, according to Charles Boyle's law, is the pressure is going to go down, and I have negative pressure, and air will move in. So it's simply contracting and expanding. How big is the pleural cavity? If the cavity gets small, pressure goes up, gases shoot out. If it relaxes, gets bigger, air goes in. So that's the world of ventilation. Now, we've addressed how does gas go in, how does gas go out, but the big question is how does gas cross the membrane? Why does it jump into the blood? Like my parents told me a long time ago. And how does the waste gas, the CO2 that I had written up here, how does it jump out and go into the lungs only, according to Boyle's law, to squish down the volume, increase the pressure, and blow it out? That's where we have to go next. So let me take another break. Let me switch some things up. We're going to get into the world of Dalton's law. I know that's exciting in just a few minutes.